are complementary to each other. To further investigate the properties of these non-vertical photocurrents, we performed a numerical analysis for one type of them, namely the linear injection current. We calculated numerically the linear injection current in pristine graphene, whereby both P and T symmetries are preserved. Here we calculate the injection current as a function of Fermi energy for fixed photon energy, h bar omega equals to 100 millieV. First, we observe that when the Fermi energy is inside the valence band or the fixed photon, there's a large peak for the linear injection current. And we denote this peak as the Fermi surface resonant current. To see how this peak arises, we first focus on the valence band, the situation where the Fermi surface is in the valence band. We find that at finite Q wave vector, as illustrated here, the transition contours for the interband transitions is tilted in K space and energy. As a result, when the Fermi surface is inside the valence band, it intersects with the transition contour, such that only half of the transition contour, indicated by the yellow curve, is below the Fermi surface and can undergo interband transition, whereas the other half is empty and is not available for interband transition. As we know that the injection current depends on the group velocity of the electrons, which takes opposite signs in the plus K and minus K space. So when only half of the contour undergoes interband transition, there's little cancellation between the plus K and minus K space. As a result, we have a large Fermi surface resonant effect. However, when the Fermi surface is near the charge neutrality point, since the entire contour undergoes interband transition, there's almost cancellation for the group velocity between the plus K and minus K part. There's, however, a very small linear injection current as shown in the inset, and this very small injection current arises from the asymmetry between the valence and conduction band, and this asymmetry arises due to the next nearest neighbor hopping, which is very small. So we only have a very small current here. To further verify this Fermi surface resonant effect, we also performed we also calculated numerically the injection current as a function of wave vector Q. Here, we first focus on the case where the Fermi energy is exactly at minus half h bar omega, that is minus 50 millieV. As we see, when Q gradually increases, the injection current also increases. This is because that, as illustrated in panel B, when Q increases, the transition contour becomes more and more tilted. As a result, half of the transition contour below the Fermi surface becomes more and more occupied at finite temperature, whereas the other half becomes more and more empty. So as a result, the injection current should increase. However, when Q becomes very large, since the transition contour becomes more and more tilted, and they shifted to opposite side of the Dirac point. As a result, the change in group velocity will decrease, leading to a decreasing current here. When Q is extremely large, due to conservation of linear momentum, there's no transition allowed, and eventually the linear injection current should vanish. Now, let's look at the red curve and the purple curve, the red curve and the purple curve, which is the case when the Fermi energy is below half h bar omega. In this case, when Q is very small and the tilting of the transition contour is very small, the Fermi surface is entirely below the transition contour, so no transition is allowed, and the linear injection current should be 0. However, when Q gradually increases, the transition contour becomes more and more tilted and starts to intersect with the Fermi surface. and then we will have some finite current due to the Fermi surface resonant effect. And the onset of the Fermi surface resonant current depend as a function of Q depends on the position of the Fermi surface. Finally, I will give some estimate for the magnitude of the linear injection current in graphene. Previous study has shown that graphene can host highly confined plasmons with very large Q, with very large photon wave, plasmon wave vector Q, and this can lead to large non-vertical currents, non-vertical injection as well as circular shift current. For the case of linear injection current, we find that for relaxation time of 1 to 10 femtosecond, the Fermi surface resonant linear injection current can reach the order of magnitude 1 to 10 nanoampere per micron. This is comparable to the circular injection current even for normal incidence with broken inversion symmetry, for example, in tungsten ditelluride and germanium sulfide. We predict that this large non-vertical photocurrent can serve as a tool for plasmon detections in 2D materials. So with this, I come to the summary of my talk. We find that on the oblique incidence of light, the non-vertical transitions, the non-vertical interband transitions can induce a finite bulk photovoltaic effect, even in materials that preserve both P and T symmetries. And the symmetry, the microscopic origin of this bulk photovoltaic effect is entirely different for the case of normal incidence with broken inversion symmetry. And this non-vertical bulk photovoltaic current exhibit a large Fermi surface resonant peak when the photoexcitation is near the Fermi surface. Last but not least, I would like to thank my collaborator as well as my PhD supervisor. Thank you for your attention.
Great, thank you very much. So we have 1 minute for questions. Any questions from the audience? You can just unmute yourself and speak.
Okay, maybe I can ask a question.
Right.
So is there a range of values where you could reasonably observe this effect at room temperature?
Yes, we predict that we can have some current in the room temperature for very large Q in graphene, but the magnitude will be small, will be quenched because of the finite temperature effect. But we predict that it's still observable even at room temperature.
Okay, we can have time for one more question from the students.
I have a question about the last slide. You mentioned about you mentioned about the relaxation time is about 10 femtoseconds, right? So
yeah.
So how do you evaluate to calculate, and what's the relaxation time?
Okay, the relaxation. Okay, this is actually phenomenological observation from previous experiments, and it is the relaxation time. It is actually the relaxation time of injection current, and it can be. Okay, sorry. I didn't have a slide for that. It is the relaxation time that depends on the scattering of electrons. So the injection current will give injection current describes some change in group velocity of electrons. It can be observed a change of group velocity for electrons upon interband transition, and it will if the electrons does not encounter any scattering, then we can have more and more larger and larger change in velocity for these electrons. But it will and as time goes on, we will have increasing increasing injection current as a function of time. However, this is not possible in real systems because the electrons can undergo scattering. And
you mean the scattering is between the electrons,
yes.
right?
Yes, it can be between electrons, but it can also be between electrons and impurities.
But for this time scale, I think it's ultra faster. Okay, this mainly comes from the. Let's see.
I think let me just summarize what Howard's question seems to be about. I think Howard wants to find out why you chose 1 femtosecond to 10 femtoseconds. Why was that number chosen? Was it plucked out of a hat or something? Where did the number come from?
Oh, I see. I think this is the typical
Is it just
value.
an example, or is it not an example?
It's just an example, but I think it's a reasonable estimate for graphene.
Okay, I guess a quick comment is that I think the reason why Seung Hao asked it because he specializes in this kind of calculations about the dynamics of ultra-fast decay or population dynamics of such systems. So he may be able to calculate the actual relaxation time given the symmetry and topology of the system. So if you're interested, you guys should definitely talk more about if there are anything that you want to be more quantitative in your estimate of the current, right? Efficiency of the conversion.
I see. We didn't really do the calculation for the relaxation.
This is the type of calculation Seung Hao has done quite a lot.
I see.
Okay, great. In the interest of time, thank you very much for the first speaker. Let's move on to the second speaker. I think it's Russell Young from Tsinghua Group, right?
Yeah. Hi, can you hear me? Yeah.
Great. Can you share your screen?
Yes, give me a moment. Okay, can everybody see the,
Yes.
Okay, yep. Hi everyone, I'm Russell. I'm working under Professor Lee Chin-Hua, and today we've been working on a project for the last 4 months, and our group studies non-Hermitian systems. And today I'll be presenting a new approach to study non-Hermitian condensed matter systems using electrostatics analogy. So here's my content for today. I'll be giving a background on why non-Hermitian systems are interesting to study in the context of condensed matter systems, and I'll then give a theoretical formulation and basis for the direct electrostatics analogy and discuss our computational flow, and this followed by a presentation of our results, as well as future conclusions and extensions to our work. So first, let's explore some background. Before understanding non-Hermitian systems, we must first understand what Hermitian systems are, and by definition, it is a Hamiltonian whose Hermitian conjugate equals itself. And in the context of condensed matter systems, this corresponds to systems with symmetric hoppings between sites. We can then impose two boundary conditions on the system, the open boundary condition and the periodic boundary condition. And one of the hallmarks of condensed matter systems is what is known as the bulk boundary correspondence, which exists in what is known as topological systems, where phase transitions are explained by discrete changes in topology. So to illustrate my point, I'll introduce everyone to one of the seminal examples in condensed matter physics, known as the SSH model. And this is a relatively simple model with very rich physics. It contains hoppings of alternating strengths T1 and T2. And this model possesses many of the key features of condensed matter systems. We can write a Hamiltonian as such, and by tuning to the parameters, one may close the gap, which generates a zero energy mode localized only along the edge. And this is, of course, protected by the winding number of the system, where if the parameter delta t is tuned below zero, it either encloses the origin or it does not, leading to the observation of the closing of an edge gap. So one way to study such systems with more insight is what is known as a band structure. And another feature we can observe in the SSH model is to compare the difference between the PBC and the OBC. In the OBC, we see the presence of an edge and therefore the existence of an edge state under appropriate conditions. However, in the PBC, there's a lack of an edge state. And traditionally, we plot the real component of the energy index against K in the first blue line zone. However, before going into non-Hermitian systems, we may also plot the energy on the Argand diagram of real and imaginary parts. And here we see that the presence of a topological zero mode corresponding to the edge between the OBC and the PBC configurations. So given that Hermitian systems given a Hermitian system, a non-Hermitian system would then be a system with asymmetric hoppings. And in a simple system, this would be leftward hoppings T minus gamma, no longer equal to rightward hoppings T plus gamma. And one effect that arises from such a configuration is known as the non-Hermitian skin effect, or NHSE, where the eigenstates decay exponentially from the system edge. And this breaks the celebrated Barb-Wanry correspondence and results in an effect we can no longer explain using topology alone. And in other words, there's new interesting physics at play. So as alluded to we can plot this more insightfully on the real and imaginary energies on the same diagram with implicit index K. And this opens up the complex plane for visualization and gives us a whole new host of techniques available for analysis. So, and we ask a natural question, which is, given a PBC Hamiltonian, how may one determine the edge effects associated with the OBC structure? And could we smoothly deform some parameter that deforms the PBC without the skin effect of the OBC? And the answer is yes. And how we do so is known using what is a surrogate Hamiltonian, introducing a deformation parameter known as kappa. And to be specific, kappa is given by the smallest magnitude-wise deformation, complex deformation of momentum K, such that eigenvalues lie at the endpoints of the PBC-OBC spectral flow. And this is nice because it encodes a formalism that allows one to model the non-Hermitian skin effect. So in essence, kappa can be treated in two ways: as a spatial rescaling, countering the non-Hermitian skin effect, or more importantly, a conformal deformation of the spectral loop in the complex energy plane. So this would be a good point to take stock of the state of affairs of non-Hermitian condensed matter systems. In Hermitian systems, we know that the most important problems can already be solved. For non-Hermitian systems, we have a formalism that encodes the generation of a PBC, OBC, and PBC Hamiltonian. And more generally, we are able to answer the question, given a Hamiltonian, what is the PBC-OBC spectrum? However, we are motivated by the inverse problem, which is given a spectrum, what would be the corresponding Hamiltonian for a PBC spectrum? And that will be pretty easy to understand. But given an OBC spectrum, it will be quite inadmissible to write a Hamiltonian associated with the OBC structure, given the non-Hermitian skin effect. And there is no way we can properly account for it. And that is the question we intend to tackle with this project. So to answer the question, let's take a look at the formalism that our team developed. So from the non-Hermitian skin effect, we know that increasing the imaginary part of K shrinks the PBC loop into the interior and forms an OBC curve in the limit. And this is illustrated with the animation as shown. So we want to answer the question, given a spectrum, how can we obtain the Hamiltonian? And the key insight is given by realizing that the statement of the inverse problem has an electrostatics analogy or dual. So to illustrate my point, we can take a look at the diagram. We express the energy as a function of momentum, where energy here is a complex variable. And this is directly analogous to a complex number z equals to x plus iy, representing the complex plane in the electrostatics problem. And next, we realize that the dual in electrostatics, where phi here is the variable to be solved for in Maxwell's equations, and on the OBC line of the non-Hermitian skin effect problem, there is a discontinuity in the gradient of kappa. In electrostatics, this happens when we have a charge density or charge accumulation along that same line. And when there is a non-zero Laplacian at the boundary, we can treat the problem using Gauss' law, and from Gauss' law, therefore obtain Laplace equation. From there, we are able to model the boundary condition of the PBC as a potential set to V equals to 0, and then solve for the charge accumulation that occurs along the PBC such that V equals 0 is continually satisfied. This charge accumulation, we then claim, is equal to the charge density in the inverse problem. So to explain that relation of the density of states to the charge density, we use the following derivable relations following from the Cauchy-Riemann relations. And these two equations are actually exactly identical in form qualitatively. So to illustrate what this is meant, we consider a set of states distributed in complex E space. And we know that each point is separated by delta K, where if we fix the number of points L, then delta K will be L over 2 pi. The exact separation of these points in E space is given by the density of the states, which practically can be found by discretization and interpolation by way of a Fourier series. And the spacing between the points is then governed by the charge density or density of states. And in this illustrative system, the circle on the left is said to have a higher density of states, while the opposite is true of the circle on the right. From this, we can infer that indeed the charge density is proportional to the density of the states up to a normalization. And using this formalism, we can find any Hamiltonian given a band structure. However, we should impose some restrictions, namely that the eigenenergies should be, or rather not restrictions, but there are certain Hamiltonians that are more sought after than others, namely those with real eigenenergies, because these are more experimentally relevant and they can be reproduced in a lab in real systems. The hopping should also be local, as local hoppings are more feasible to achieve experimentally. So now we take a look at the results using the formalism we've put in place. So to test our methodology, we impose it on the simplest non-Hermitian model known as the Hartano-Nelson model. And it's a simple asymmetric matrix with diagonal elements, U not equal to V. And while simple, it should not be taken for granted because it emits an analytic solution of the OBC line equal to 4 square root UV. And the reason we start off with the Hamiltonian here beforehand is because we should know what the band structure should look like. We then make a continuum approximation in the large side limit and impose the electrostatics problem as such. Solving it yields the following density of states along the arc length of the ellipse. We discretize the set of points L along the ellipse of the PBC separated by constant K, whose separation in energy space is governed by the density of states, which has been solved for previously. And this gives us an explicit Hamiltonian in terms of the Fourier series. Unsurprisingly, when we plot the Fourier series, this recovers the original band structure, and the Fourier series itself contains coefficients U and V, which quantitatively agrees with the original band structure. So we further analyze whether the skin effect is present, and we do this by plotting the value of the eigenstates of the system against each side. And we see that the exponential decay from the system boundary that characterizes the non-Hermitian skin effect. And doing this for all sides allows us to verify kappa, otherwise known as the decay length e to the minus k, kx, along each side. And we're able to recreate one of the cornerstone effects of non-Hermitian systems with boundaries. So we then plot the decay length for every side in the OBC, and we find that they qualitatively agree with the shape of the specified voltage. Yeah. So we repeat the same for a variety of Hamiltonians, namely z plus 1 over z squared, we follow the same scheme. And here we learn an important lesson, which is that when we have rotational symmetry to exploit, one may cut the band structure into equal pieces. And in this case, there are 3 petals to this flower. So each petal will correspond to an interval of 2 pi over 3. And we can express each petal as a Fourier series in order to improve convergence, therefore dealing with the discontinuities in the system. And plotting the final result, we see that the agreement is good and we're able to reproduce the original band structure. So next we proceed to understanding how the 2-band SSH model behaves. And this is an important model to study as it most well understood of all 2-band models. And we start again with the known form of the Hamiltonian with the goal of reproducing the band structure. We solve the electrostatics problem, and we then solve the momentum band structure with a 1-band assumption. And we note that this 1-band assumption doesn't quite yield the result that we want. And this is because of a theorem in Fourier analysis that says that where branching occurs, that the convergence is as the power series, not as an exponential. And this is a very important subtlety for anyone who wants to reproduce our results. So to deal with this, we cannot use a 1-band assumption, but instead we have a 2-band model or ansatz. And to fix this problem, we write the Hamiltonian in 2 bands. And here we have the privilege of knowing that the SSH model is a 2-band model a priori. But suffice it to say, we can expand the energies E squared instead of E. And this is useful when E is non-local, but E squared is local. And notice here that when we plot the momentum band structures once again, that the period has sort of doubled, which is reminiscent to E squared. And we plot the final band structure in terms of this Fourier series, and we see that we have recovered the band structure successfully. So on to my last example. We tackle a system in which no one has ever written down a Hamiltonian before, And we start by imposing two disjointed OBC lines on an ellipse, where each line has unequal voltages or potentials or density of states, which will then correspond to unequal potentials. If we will be able to recover the Hamiltonian for this example, this will act as a proof of concept for the formalism developed. We set up the problem with the arbitrary length scale. And here are the density of states when we solve for. We then move on to plot our momentum band structures, and we realize again that the result doesn't quite agree. And we solve, and this is a technical point because this is purely a convergence issue, not theoretical of one to do with the formalism. So to deal with this, we introduce a trace term as well as our two-band model. And using the characteristic equation for eigenvalues, which correspond to energy, we notice that we have two sets of solutions. We discard the solutions which are not relevant, corresponding to E minus 2t, leaving us with eigenvalues lambda equals to E. And this is when we can use it. So here we see the result. And we see that we reproduce a good fit, and we can obtain the Hamiltonian in terms of a Fourier series. So here are the summary and techniques that we have learned so far, and we have developed to improve convergence. So in conclusion, this is the significance of our work. We are able to retrieve the Hamiltonian for any spectrum or band structure arbitrarily, and these Hamiltonians do not need to be restricted to PT symmetry for real spectra. So as extensions, we're working on experiments as well for future work. Yep, and that concludes my presentation.
Great, thank you. Question time.
Hi, Russell. I would like to ask a question.
Yes, please.
So actually, I would like to understand the context of one band and two bands, because SSH model is already a two-band Hamiltonian. So what is the context of one band and two band?
So you're saying in the context of implementation of this, is it?
Yes. Yes.
Okay, so we note that when we have SSH is already two-band, and you're right. However, we cannot impose one band ansatz on a two-band model at convergent. The model that we're dealing with is two-band, and this would help to improve convergence due to the square root term in the Fourier series. Yeah, so in this case, we know the SSH is already a two-band model, therefore we impose a two-band ansatz on it. But in general, for very generic systems, if we draw an arbitrary band structure and we ask the question, what is the Hamiltonian? We probably won't know whether this system is one band, two band, three band. So we probably need to guess, starting off with a one band model, or the convergence doesn't quite work. We then move on to a two band model, and if it doesn't work, we add a trace term. So these are techniques used to improve the convergence of the system.
I see. Thank you.
Okay, any other quick questions? Okay, if not, in the interest of time, let's just move on.
All right, thank you.
Yeah, thank you. And also, so if the audience have any questions, right, feel free to send a private message to speakers. And it's also good for the speakers to know you as well. Unfortunately, we can't be sitting in the same room, right? But feel free to discuss with the chat window. Okay. All right, so our next speaker is from Professor Feng Yuanping's group, I believe, Youjing Yang. Can you share your screen?
Yes.
Great. Okay, you can start.
Good morning, everyone. My name is Youjing Yang from Professor Feng Yuanping's group. I'm glad to represent our recent work here, two-dimensional topological superconductivity candidate in a one-device layered material. My report is divided into the following parts. First, I will give a brief introduction of 2D materials. Then I will introduce a 2D topological superconductivity candidate tungsten nitride. Finally, I will give a summary. Two-dimensional materials have been extensively studied due to their intrinsic properties such as magnetism, topological states, and superconductivity. Among these 2D materials, single atomic layer materials are particularly fascinating because they can be easily foliated from their finalized materials and can be constructed into multifarious heat structure to realize complex and extraordinary physical phenomena. In 2D systems, magnetism with non-trivial topology can induce unusual behaviors. One example is the quantum anomalous Hall effect, where the combination of strong spin-orbit coupling and ferromagnetic ordering can generate a band gap in the bulk and gapless chiral edge states at boundaries, and the quantized Hall conductivity is carried by the edge states. The topological phase of superconductors has recently received intense research interest as the superconducting quasi-particles residing in the non-trivial gapless boundary states are considered a form of Majorana fermions. The emergent topological superconductors with Majorana fermions are thought to be useful for fault-tolerant quantum computation. Topological superconductivity was proposed to be induced in topological boundary states of heat structures composed of topological materials and superconductors by proximity effects. However, the interface conditions dramatically influence the observation of topological superconductivity. Therefore, discovering 2D materials with simultaneously superconductivity and non-trivial topology will be of great value to achieve topological superconductivity. Although several 2D superconductors have been reported, very few of them can exhibit topological states. So a crucial issue is to fabricate novel 2D materials with simultaneous superconductivity and non-trivial topology, while one-to-one materials may play an important role. Next, I will introduce our recent work on two-dimensional topological superconductivity, a 2D topological superconductivity candidate W2N3. The bulk W2N3 has a one-to-one layered crystal structure with AB starting along 0001 direction, which was synthesized in 2012. The monolayer tungsten nitride is composed of inversion symmetric layers with two 1T nitrogen tungsten nitrogen layers sharing one layer of nitrogen atoms. It can be easily exfoliated from its bulk material due to the low exfoliation energy of about 46 millieV per atom, which is much smaller than that of MOS2. In this figure, we plot the electronic structures of monolayer tungsten nitride without and with spin-orbit coupling. It is noted that the spin-orbit coupling removes some degenerate points and significantly changes the band structure because the heavy tungsten atoms possess relatively large spin-orbit coupling. So our results discussed in the following was calculated with spin-orbit coupling included. The band structures present many interesting features. First, the spin-orbit coupling leaves the degenerate point at 0.5 EV above the Fermi level, leading to a non-trivial band topology characterized by a topological invariant Z2, and Z2 equals 1. Both without and with spin-orbit coupling, the well point at about 1.5 EV below Fermi level at K or K prime points are stable, which are protected by the symmetry at K or K prime points. Third, it is interesting to note the two-fold band degeneracy along the high symmetry lines, gamma 2M, both without and with spin-orbit coupling. Fourth, there are several one-half singularities in the band structure, leading to a sharp peak of density of states. In particular, the one-half singularity at about 0.1 EV below the Fermi level, which brings about high density of state near the Fermi level. These non-trivial topological states are fully reflected in their surface states as shown in these figures. There are 3 flower-shaped Hall pockets labeled as S gamma 1, 2, 3 from the inside out, and 1 electron pocket labeled as S gamma 4 around the gamma point. At the center of the boundary of Brillouin zone M are elliptical hole SME and electron pockets SMR. The metallic property with high density of states near the Fermi level motivated us to investigate the possible superconductivity. The absence of imaginary frequency modes indicates the dynamic stability of molar tungsten nitride. From the projected phonon density of state, we find that tungsten atoms vibrate in the low frequency region, while nitrogen atoms vibrate in the relative high frequency region because they are distinct atom masses. And the phonon vibrational modes of tungsten and nitrogen atoms are separated by a phonon spectral energy gap of about 6 millieV. From the cumulative frequency dependent electron phonon coupling, we find that the low frequency phonons from the vibration of tungsten atoms account for 74% of the total EBC, and the total electron phonon coupling is about 1.47. Utilizing our calculated electron phonon coupling together with a typical value of the effective screened Coulomb's repulsion constant 0.1, the superconducting transition temperature is calculated to be about 21 Kelvin with the Macmillan-Allen formula, which is the highest reported for 2D superconductors exfoliated from van der Waals bulk materials. In this figure, we plot the quasi-particle density of state in the superconducting state at two representative temperatures of 6 and 18 Kelvin relative to the density of state in normal state as a function of the frequency based on the anisotropic middle and Ashbrook's theory. We can observe that the superconducting gaps at 6 and 18 Kelvin are about 5 and 4 millieV respectively. In this figure, we plot the temperature-dependent superconducting gaps as well as the BCS fit, the red dashed lines. It is seen that the superconducting gap vanishes around 22 Kelvin, and the zero temperature superconducting gap is about 5 millieV. In these two figures, we plot the momentarily reserved superconducting gap and electron phonon coupling on the Fermi surface. On the whole Fermi surface, there are finite superconducting gaps, indicating the Fermi surface is fully gapped below TC. It is noted that the superconducting gaps are highly anisotropic. The regions of the Fermi surface with the largest superconducting gap coincide with the largest electron phonon coupling strength. So we can conclude that the high TC and the large superconducting gap in molar tungsten nitride are mainly from the strong spin-orbit coupling of the Fermi surface around the gamma point. It was mentioning that due to the exceeding strong spin-orbit strong electron phonon coupling, the normal state of molar tungsten nitride may be a non-Fermi liquid. From the calculated specific heat, we find that the specific heat displays distinct features. At low temperature, the specific heat satisfies the exponential relation of temperature, which occurs with the low temperature specific heat of BCS superconductors. And temperature between 20 to 80 Kelvin, the specific heat follows the third power of temperature. And at a high temperature region above 80 Kelvin, the specific heat is proportional to the temperature. It's clear that below 80 Kelvin, the normal state shows a non-Fermi liquid behavior. The Lorentz number can further verify this observation. We can observe that the Lorentz number is not a constant at temperatures below 8 Kelvin, which dramatically violates the Wiedemann-Franz law, while at high temperatures, it shows almost a constant, indicating Fermi liquid behavior. The relative thermal conductivity is given in this figure. It can be observed that at temperatures lower than 2000 Kelvin, the slightest thermal conductivity dominates, while at temperature above 2000 Kelvin, the electrical thermal conductivity makes more contribution. The largest thermal conductivity mainly comes from the vibration of tungsten atoms, that is the most from 1 to 6, because of their longer phonon lifetime. So the nitrogen atoms contribute little to the thermal conductivity, leading to the low thermal conductivity of monolayer tungsten nitride. The spin texture of the Fermi surface is also calculated in this figure. It is noted that the H Fermi line is fully out of plane, spin polarized, indicating an Eschen type pairing in monolayer tungsten nitride. This result is similar to the superconductivity in ion-gated MOS2. However, the magnitude of spin moments is different at different key points on the Fermi surface for monolayer tungsten nitride. The spin polarization direction between the outer and inner Fermi surface is inverted at the degenerate points on gamma 2m path, at which spin up and spin down are cancelled. Now I will summarize the report. We report that a 2D monolayer tungsten nitride holds simultaneously the topological state and the superconductivity. The monolayer is found to exhibit different topological states and different energy levels based on anisotropic Mendel and Aschenberg theory. The monolayer tungsten nitride is predicted to be a phono-mediated BCS superconductor with a superconducting transition temperature Tc of about 22 Kelvin and the superconducting gap of about 5 millieV. Both the superconducting transition temperature and the superconducting gap are the highest reported in the 2D superconductors. It's foliated from its bulk, is one of its bulk material. The high superconducting temperature and the large superconducting gap are unveiled to be from the enhanced electron phonon coupling near the Fermi level at gamma point. Due to the large electron phonon coupling, the normal state of monolayer tungsten nitride performs as a non-Fermi liquid at temperature below 80 Kelvin, while the electrical specific heat displays a cubic behavior of temperature, and the Wiedemann-Franz law is dramatically violated. That's all. Thank you for listening.
Okay, thank you. Questions from the audience? Any questions? We do have a bit of time. Okay, maybe I'll just comment on behalf actually of my postdoc, Christian, because my postdoc Christian is developing a formalism for calculating the Higgs mode in superconductors, especially in 2D superconductors with non-trivial geometry and topology. So I wonder if there's something that you guys can learn from each other and do something together as well. I don't know if Christian is here. Any comments? Maybe he's not here. Okay, but anyway, so you are studying 2D superconductors in a topological system. So if you're interested in exploring some calculation relating to the Higgs mode as the oscillation of the order parameters. Yeah. I'll let Christian know as well. Okay, any other comments or questions? Okay, if not, let's move on.
Thank you.
Let's move on to the next speaker. I believe the next speaker is from Shafiq's group. Naya Banta, can you share your screen? Great. Okay, you can start.
Yeah, so you all can see my screen, right?
Yes.
Yeah. Hi everyone. Today I'll be presenting our recent work actually showing the evidence of many body localization in 2D from quantum Monte Carlo. So if you are more interested, you can take a look at actually this preprint. And yeah, so I'm Navant, and this work has been done with my collaborators from Anyways, NTU, and also people us from Germany. So okay, so let's dive in directly into the many-body localization. Just to give an introduction, so disorder plays a key role actually in these systems. And as Anderson has shown, in the absence of interaction, wave functions can localize, and this is the very well-known phenomenon of Anderson localization, where wave functions can localize actually exponentially over some localization length. And for weak disorder, and there is a dependence on the dimensionality, we have these two distinguished phases, localized or extended kind of states, or delocalized phase. Now, to bring in the effect of interaction is important, because many of the condensed matter systems interactions are there. However, this interaction actually brings into non-trivial physics, and one of the manifestation of interaction leads to this phenomenon of actually many-body localization. So just to very briefly say, it really shows very distinct kind of behavior. Okay, just to mention, it's it violates the eigenstate to ETS hypothesis. Okay. And then it also shows actually the area law of entanglement entropy, which is behavior of ground states in general. But here we can see the area law even for excited states. Now, for most of our studies, we'll actually use this Hamiltonian. So I just want to highlight actually here. So here these are actually the spins on a lattice, which couple through this Heisenberg interaction. And here this term is actually the local disorder kind of magnetic field, which couples to the spin SC components. Okay, so there have been studies in 1D which saw this actually interesting phase diagram where the x-axis is the disorder, the y-axis shows the full spectrum. Okay, starting from somewhere here is the ground state to the the peak. And for main MBL studies, usually one is interested somewhere in the middle of the spectrum, and it actually gives the interesting behavior. Okay, so okay, now okay, so in the there is a kind of lot of work actually for MBL actually in 1D and 2D. Okay, while its existence in 1D is well established, like the previous phase diagram that I showed is for 1D calculation. Okay. However, in 2D, it has been very inconclusive. There are actually theories showing it exists, and there are actually which so-called actually it doesn't exist. And one particular scenario, which actually the next talk is about, it's conjectured that this so-called scenario of thermal avalanche, which actually kills many-body localized phases in greater than 1D. So some of the recent studies which claims to find 2D MBL study here. However, these studies are not as rigorous as many of the 1D studies, where it has been definitively shown that the existence of many-body localization. Now, on the experimental side, there have been also several experiments which seem to indicate actually the existence of 2D MBL. And what they suggest actually the MBL transition in 2G is very similar to 1D, okay, which is a rather so-called unexpected actually when we look at the theory side. And one thing actually in experiments suggests that there exist rare regions which make the probing quite challenging in the so-called experimental time scales. Okay. Also, the experiments are done in very specific model, and so there has been actually this is a very kind of debatable so-called actually thing whether to claim that 2D MBL exists or not, and that is where we kind of decided to do the calculation and see whether we can provide actually strong evidence of existence of MBL. Okay, now. No, since we talk about 2D, what are some of the theoretical challenges? So definitely, if we look at exact diagonalization calculations, we know it is limited to small system sizes, and working 2D will be very challenging. And there have been other calculations of studying behavior of local integrals of motion, and also studying so-called eigenstate behaviors using tensor network approaches. However, this kind of studies, even though it is important to have actually in the absence of any detailed kind of theory, but these are kind of they have their own limitations. And in that way, to come up with a completely unbiased kind of numerical calculation will be really very much actually necessary. So for our approach, we kind of used in a sense a combination of quantum Monte Carlo technique with another technique which we call the eigenstate to Hamiltonian construction approach. So let me just very quickly mention actually what. So the quantum Monte Carlo, we actually, for our case, we used something called the stochastic series expansion method, which is well established in the kind of literature, and it is known to study actually the kind of spin systems on lattice very well. However, this QMC, we can actually obtain the ground state and study the phase transitions in the ground state. Now, having obtained the ground state, we use this eigenstate to Hamiltonian construction approach to map these ground states, okay, and find actually so-called new Hamiltonians or target Hamiltonians for which our ground state is an excited state. So in that way, combining this quantum Monte Carlo and this EHC technique, we are able to study the behavior of eigenstates. Now, this is numerical calculation. So for small system size, we also use hexadiagonal calculations to benchmark our QMC results also. Okay, so just for those who have not seen actually about or heard about the stochastic series expansions, it's a finite temperature quantum Monte Carlo technique. However, we can find actually the details of ground state properties very efficiently. One of the main reason also to use this one is there have been debates about the previous studies which claim to show existence of 2D MBL. Those are done on very small system sizes. And with our approach, we can really go to system sizes very large. In fact, one or so yeah. So that's one of the reason also why we kind of try to use this QMC technique, and also we can do large disorder average, okay, to study actually detailed sampling. And some of the key observables we measure here also gives definitive signatures of the localized and delocalized behavior. Okay, so just to start with so-called behavior of ground states. So we look at the so-called spin stiffness. This actually tells us whether our ground state actually is localized or delocalized. So for a disorder Heisenberg model, it is known actually the ground state has two phases. One is the superfluid phase and the other is the Bose-Glass phase, which is the Bose-Glass phase is a localized one. Okay, and the stiffness is actually 0 in this case. And we do a finite size scaling to find out exactly where the transition lies, and more details are there actually so in the preprint. Also, just to highlight actually the delocalized and the localized phases in the ground state, these are very different signatures if you look at the local magnetization distribution or even the local entanglement entropy. Okay, so I'll just very quickly move to the main part is studying the eigenstates. Now, as I mentioned, MBL is actually the behavior of the highly excited states, or in general, the eigenstates, okay? So after obtaining our ground state, we use the so-called this eigenstate to Hamiltonian construction approach, which goes like this. So we start with this actually parent Hamiltonian, okay? Or the so-called our original Hamiltonian. And with QMC, we obtain its ground state. Then from your ground state, we actually construct something called this quantum covariant matrix. Okay, and from this, as we find actually the quantum covariant matrix, the dimension is much smaller than actually the so-called the original Hamiltonian, which is 2 to the power order, 2 to the power n, with the n is the lattice side, whereas the quantum covariant matrix is much smaller actually. And this really helps a lot in terms of the numerical diagonalization based studies. Okay, so once we obtain the so-called quantum covariant matrix, we can diagonalize it and study its eigenspectrum. Okay, and the eigenvectors of actually the covariant matrix gives us the new Hamiltonian for which we want to know actually our this ground state, whether it is a what energy it corresponds to. And one tricky thing actually, okay, so this is not the first time we have been using this technique. So this has been used for actually a 1D scenario. However, the space of target Hamiltonian, it increases significantly in the 2D. Okay, so in that way, numerically simulating this was actually quite challenging. So, okay, so here I just want to, so actually, okay, so the quantum covariate matrix looks like this. So in that sense, it's a variance of actually this, energy actually, for this Hamiltonian, just to say. Now, once we diagonalize actually, and let's say these are the so-called eigen, so these are the eigenvalues. So then it has two trivial eigenvalues which are 0, and this corresponds to the original Hamiltonian for which the energy variance actually is 0, and the other one is the total magnetization. We work in a so-called constant Hilbert space. Okay, so in that way, the E3 is the so-called okay. In this scenario, it will be E2. Okay, yeah. So that will be in the sense actually our so-called non-trivial so-called eigenvalue. And then we use actually the psi3 corresponding to E3, which gives us the so-called this target Hamiltonians, like the couplings of the target Hamiltonians. So even before going to that, so let's look at just the behavior of the E3 here. So here we show actually the, again, system size dependence and like that. So we can see there is a, since this is a log scale, this shows a power law decay, the E3 averaged actually over disorders. And this vanishing of actually E3 kind of establishes that in the thermodynamic limit, this will be 0, and we'll be able to find the so-called the exact the so-called correct new Hamiltonian. Okay. Now here we show actually our phase diagram in the main result. So okay, so from E3 actually we saw it thermodynamic, it vanishes. The corresponding eigenvector gives us the new Hamiltonian, which has the same form as our actually so-called original Hamiltonian, except it has the different couplings. Okay. Now we calculate actually this. So okay, so all these is still the, the couplings for individual disorder will correspond to very different values, which are the signatures of different disorders actually behave very differently. Okay. However, just to obtain this phase diagram, we rescale actually the energy corresponding to this actually so-called the excited state. Okay, so in a sense, the psi naught for the so-called the ground state of our original Hamiltonian will be excited state for S tilde, and its energy is found in this way. Okay, and also for the disorder one, so since actually we are have very different disorder samples, in fact the distribution is very different, unlike our so-called initial disorder, which is a uniformly disorder sample. So we actually calculate something called the typical average. Okay, so if you look at the right hand side, so here this is the rescaled energy versus the typical average phase diagram. So in a sense, we have obtained the ground state from QMC, and we want to show actually, what energy this ground state will correspond to as we move actually in this kind of, the energy axis. Okay. And we show it for two different kind of values, but we can do actually it for certainly for the deep in the so-called this localized side. Also, we saw actually this the formalism, this ESC formalism actually works also the delocalized side, which actually is not shown here. Okay. Now, going forward, we want to kind of understand some of the things whether this okay. So here the calculation shows definitively in a sense we do have MBL in 2D. Okay. Now the question is actually is are these states stable? Why this ESC even worse? So the thing is it is still actually ongoing work. But what we found actually the so-called the new disorders are highly correlated in contrast to the original disorder that we can so which is highly kind of so-called random. Okay, and then also to propose a mechanism why this MBL actually is stable in sort of the 2D. Okay, because in 1D it has been fairly understood, but what we observed that the 1D mechanism, which says the presence of weak links, it doesn't hold for 2D because we need a several ring of actually weak links to have this kind of phase, which is certainly not possible. Okay, so we are trying to come up with a different mechanism, and this is also ongoing work. Okay, so just to conclude here, actually, so with our this combined quantum Monte Carlo and the ESC approach, we conclusively show the presence of MBL in 2D. And as I mentioned that, the weak links are not responsible for actually the 2D MBL, rather it might be the non-ergodicity, which is a rather kind of, so for more plausible kind of mechanism. And just to highlight also, this method can be actually applied to 3D and study also different Hamiltonians actually. Okay, so before I end, I'd like to along with my collaborators, I'd like to acknowledge the contribution Gabriel, who is here for his valuable discussions, and Miguel, who helps us computationally, and also like to thank the computational resource from NSCC and the C2DM clusters. So with that, I will end and I will take any questions.
Okay, thanks. Any quick question? We're running out of time a bit. If not, let's because the next speaker is from Daryl, who is also going to talk about the many-body localization. So maybe after that, we can direct questions to both speakers. Okay, so Daryl, can you share your screen?
Sure.
Okay, great. You can start.
Right. Okay, so this is many-body localization part 2. I'll be talking about thermal avalanches, and so most of my talk will be covering old theory just to bring us up to speed, and then there'll be a small section at the end, which is stuff that I've done and stuff that I'm hoping for. This is very much work in progress, but to start off with this, just to recap the state of affairs, this has been brought up by Naipan previously. 2D MBL has been observed in both experiments and numerical simulations, but the results remain contentious due to the thermal avalanche conjecture that suggests that MBL is generically unstable in dimensions higher than 1. So what is this thermal avalanche conjecture and why is it so dangerous? Generally, critical disorder strength is necessary for localization if interactions are present. So we're talking about MBL, of course. In any disorder configuration, there may be rare regions of low local disorder. And in these rare regions, it's possible that they may host or spontaneously generate what we call a thermal bubble. And under certain conditions, this bubble may grow and destroy localization in the entire space. So what is this thermal bubble and why does it grow? A thermal bubble is a collection of thermal spins and the associated cloud of energy levels. If this is just a subset of the system that is well described by the eigenstate thermalization hypothesis, which is somewhat tautological, but just bear with me. If this bubble couples to and manages to thermalize an adjacent spin, well, the bubble was ergodic, so if it manages to thermalize an adjacent spin, bubble plus spin is ergodic, total system is ergodic. The addition of this single spin doubles the Hilbert space dimension and halves the level spacing, which makes the total system an even better thermal buff than it was previously. And because it's only getting better, this total system will then act as a buff for the next localized spin. This is a very rapid overview of the theory, and I will now proceed to go into slightly more detail. So, bath hybridization. On the left in red in both figures, we see the level spacings of the thermal bubble. And it's somewhat random. When it couples to an adjacent spin, there's a perturbation, and this causes a splitting of the levels into bath plus spin. So on the left, we have very weak coupling. On the right, we have very strong coupling. For small coupling, your new eigenstates are basically the outer product of the old states, bath and spin. So we can solve this system using perturbation theory. The new states are separable products of old states. Therefore, this adjacent spin, which was localized and had memory, can retain its memory. And so this does not lead to the thermalization of the spin. For large coupling, however, the eigenstates are more mixed together, proper hybridization occurs, and you are able to thermalize the spin. For dimensions greater than 1, the density of states of spins at a radius r from the bubble increases with r. So the bubble is better able to thermalize additional spins the larger it grows. Now, I've said small coupling, large coupling, and that's partly inspired by this diagram here, but small compared to what, large compared to what? We are comparing the coupling to the level spacing. And the level spacing is actually the more important thing here. So small coupling means large level spacing, large coupling means small level spacing. So talking about the level spacings, delta, every spin hybridized into the bubble decreases the average level spacing by half, if it's a spin half, by a third if it's spin 1. So decreasing the average level spacing for a fixed coupling strength makes it easier to hybridize every successive spin. So increasing the dimension, of course, increases the density of states of spins at a particular radius. And so having a higher dimension and being able to thermalize more spins means that you are more likely to thermalize the next spin. And this is why it's called an avalanche. Like once it starts, there's no stopping this train. Except there's one thing that stops it, which is the coupling. Now, the coupling is usually taken to decay exponentially. This coupling is related to the square of localized wave functions. And it's been accepted, shall I say, that localized wave functions have an exponential tail with decay length c, which we call the localization length. And so this decaying coupling is the only thing that is stopping the growth of the bubble. We can combine these two points together and get a single avalanche condition. So the first bit, this AD R to the D over 2, that's the density of states from adding increasingly large numbers of spins into my thermal bubble. And the second term is, of course, from the decaying coupling. From this condition, we see that for D equals 1, D equals 1 is critical, and there exists a critical localization length such that avalanches do not propagate at all. If C is sufficiently small, we get that this exponential is purely decreasing for increasing R, and this bubble cannot propagate. For any dimension greater than 1, instead, a critical R star exists such that any bubble larger than R star grows without bound. However, the fact is, people claim, including us, people claim that we observe MBL in 2D. So why do we observe it? Well, the level spacing hybridization term is fairly robust and not something I feel like attacking anytime soon. However, this assumption of exponentially decaying localized wave functions, that might be tenable to attack. So where does this idea of exponentially decaying localized wave functions come from? It's derived from random matrix theory, but I hear some. Shall I continue? Never mind. So this exponentially decaying localized wave functions are derived from random matrix theory, but random matrix theory itself has its own set of assumptions. Particularly, they assume that the external potential your particles are in is purely random. And that's never the case in experiments. You always have an external applied potential. For example, in optical experiments, you set up an optical lattice and then apply speckle disorder on top of the optical lattice potential. So might it be that including this external potential may change the results some way? Might it change the localization profile? Well, in order to set this up, to look at this, investigate this, I bring up very single physical particle model. This is just Schrodinger's equation in a very simple form. Our external potential is broken up into two parts. We've got a lattice potential and our disorder, W. We look at the state with lowest positive energy. So if you notice, I've set it up such that my external potential is purely negative. So a positive energy means this is a very excited state. So we are interested in these excited states. So this is where we're looking to see localization. The energy scale is set by the kinetic term. Just pick a disorder strength. Let's say 4, just to make things nice and visible, and scan through V0. So for V0, we know that random matrix theory tells us the wave function should decay exponentially. Let's see what happens as we increase V0. So when V0 equals 0, this is what the log of the absolute value of the wave function looks like. And we can see it's basically an inverted absolute value function. So that means, yes, this wave function is exponentially localized. However, if we increase V0 to say 20, we get a much more gentle slope. And might be arguable that this is better described by a parabola than in. So what we do then is this is for a single disorder configuration. So what we do is we perform this experiment, we perform this exact analyzation many times with many different disorder configurations. And for every single time, we try to fit it to either a downwards parabola or a downwards absolute value function. From that, we obtain what's called R squared. This R has nothing to do with the radius. This is the coefficient of determination. It basically tells us how good a fit is the model to the data. And we ask it, okay, which of these models are a better fit? Is the exponential a better fit, or is the Gaussian a better fit? And we can see that at very low V0, exponential is the better of the two models. There's a little bit of noise. R squared isn't fantastic because of the random potential causing a lot of these ups and downs, which causes the mismatch. But exponential is better for V0. We can see that. Gaussian is actually quite terrible. But as V0 increases, and the effective noise gets smaller and the jaggedness gets smaller, we can see that we've decided that Gaussian is a better fit to this data than exponential. So might this potentially modify the avalanche condition? So instead of R over C, we have R squared over C squared. And this would make D equals 2 critical, which means that MBL can indeed be seen in 2D. So this is the extent of where I've gotten. We'll be doing a lot more work to try and solidify and pin down the things that I've been talking about, but we're very excited about this. And thank you very much for listening.
Okay, thank you. Okay, so now we can ask questions to both speakers, Nayapanda and Daryl. We have quite a bit of time here. Any questions from the audience? Maybe I'll just start with a comment, actually. So is it true that for these studies of many-body localization, one of the main bottlenecks is, from a numerical point of view, is try to increase the system size? Since here you're trying to distinguish between Gaussian distribution, Gaussian decay, and an exponential decay. The signal is not very clear, but will a larger system size help, actually, here?
It should, but I mean, a larger system size will generically help for many things. But especially so in a single particle like Schrödinger equation, system size is not important because it scales linearly with the discretization of space of your wave function. But if you want to add in interactions, then real space is not the best description or not the best way to write these wave functions in. You want to look at Fock space, and then when you're in Fock space, it scales either. So if you've got very few particles, if you've got a very dilute system, it scales algebraically with the number of particles, and if you've got a very densely occupied system, then it scales exponentially with the number of systems, and that's just basis states. And then your H, of course, is number of basis states squared. So there's really an explosion in memory requirements when you increase system size. So for the previous model that Nayaban was talking about, that spin model, just increasing it by 2 particles, you're going from 8 choose 4, which is 70, to 10 choose 5, which is substantially more. And if you want to do more than that, 12 choose 6, 14 choose 7, 16 choose 8. It's exponential.
Okay.
And with every additional particle, so that's really quite nice.
Okay, can I just comment very briefly?
Sure, of course.
So, Angbo's comment, yes. The bigger system size, we can say the signatures will be very clear, and that's in a sense the wish really. Even for 1D, so far exact diagonalization, which is really the most accepted kind of, has seen that existence of MBL. I think people have gone to 24 or maybe, and sometimes maybe using some special techniques slightly higher than system sizes, okay? For 2D, I think unfortunately that's not the case. So in a sense, the bigger system size one can do, the signatures will be more clear, especially if you are looking at this label statistics and some of those signatures. So yeah. That's the main reason, like, why. And in fact, some of these 2D studies before us, like the tensor network, actually, one of the main criticism to accept those kind of results is because these are done in a very small system sizes.
Yeah, so I'm asking because I also have some kind of random thoughts about this system sizes. So I wonder if there are more like exotic or modern approaches in dealing with many-body localization, which is purely quantum system, some kind of annealing problem. I know Tsinghua was looking into quantum computer. Now it's accessible now with using quantum computers from IBM, etc. Right? Are there any research in trying to use, for example, quantum computer to deal with many-body localization and the issue?
Okay, so the one, if you say by quantum, this is qubits, right?
Yeah.
Yeah, so I think for 1D, it has been shown, like there are, like, I think people even security in NUS, they have shown. There have been other groups actually which have shown, but I think all these are actually 1D kind of scenarios actually.
So why is 2D more difficult? Because they don't have enough qubits for such calculations.
I mean, my rough probably claim will be yes, that. I'm not sure. Okay, that's like Gabriel, who might be more experienced or expert like that, he can comment also on this.
Okay, it's just some random thoughts.
Yeah, okay, thanks.
Okay, any other questions before we move on? Okay, if not, let's thank both speakers. Let's move on to our next speaker, Sativa Singh from Marco's group. Okay, can you share your screen?
Yes, please.
Great.
So my screen is visible?
Yes, great, you can start.
Okay, thank you so much. I'm Satvir Singh. I'm a research fellow under Professor Marco Betado. And my present talk is on discrete method for multidimensional transport problem. Okay. Sorry. So generally in transport of the quasi-particles in solid is the basis of many modern technology, such as chip technology or semiconductors. So aim of this study is to investigate the quasi-particle behavior in various multidimensional materials, strongly out of equilibrium dynamics, interaction with terahertz radiation. The interesting application is ultrafast thermalization, ultrafast spin transport, spintonic terahertz model, microscopic quantities such as diffusion coefficient and activity. So this is the Boltzmann transport equation where F is the distribution function which presents the probability of quasi-particle to occur at position x, momentum k, and time. For left hand side, this is the where V of x is the velocity in real space, which is given by the gradient of dispersion relation, and V of k is the momentum in space. And this is the scattering term. So in our group, we have few persons are solving this Boltzmann transport equation. This left hand side is the transport part, and this right hand
Is it just me? I can't hear the speaker.
Yeah, I can't hear the speaker too.
I have the same problem.
Same problem.
Okay. Sativa, I think it's a network issue. We can't really hear you.
Sativir.
Yes, Marco.
Yeah, so there are some connection problems. Maybe can you use some wired connection? Are you using the Wi-Fi?
I'm using Wi-Fi here. And I'm home actually.
Okay. Okay, let's try again. So continue then let's see.
Still my voice is breaking?
Well, sometimes the connection was going away. But okay, just continue and then let's see.
Okay. So aim of the present work is to develop multi-dimensional numerical solver for solving Boltzmann transport equation in strongly out of equilibrium condition. And to test the transport part in Boltzmann transfer equation, we are using reaction time approximation. We will type some analytic solution for 1 or 2 dimensional Boltzmann transport equation. And finally, we will present some numerical results. So what is the difficulties in modeling of Boltzmann transport equation? At first, this is high dimensional, it is 7 dimensional. It means 3 dimensional is spatial, and 3D in momentum and 1D in time. Secondly, it has some intrinsic physical property such as non-probable momentum energy dispersion. It has some, it should have some conserved property like mass, moment, and energy. It has some difficulty in time step restriction and of course in complex scattering term. So which type numerical solver is applicable for this type problem? We have 2 type approaches. One type is stochastic approach, and second we have some deterministic approaches. In particle stochastic approach, we have 2 type of method. One is called Monte Carlo, and second is spherical harmonic expression. Main drawback of this method, it creating some numerical noises. On the other hand, we have some CFD-based method like finite difference, finite volume, finite element, and the spectral method. In this method, I am working on one of them, spectral method, that is called discontinuous Galerkin method. The main advantage of this method, it has strongly mathematical support. It has HP adaptivity, very compact scheme. It is applicable for any type of masses, and it is highly efficiency for parallelization. How it works? At first, we will write the Boltzmann equation in that format, in Geneva format. Then we will go for domain decomposition. Then we will go for approximation solution in terms of degree of freedom and basis function. Then we will find some residual. And after that, we will multiply the test function into residual function to vanish locally. Then we will apply some Green-Gauss theorem. And in this way, we will get the all elements are disconnected. So we have to come into the finite volume approach. In this approach, we will introduce some numerical flux. And after that, we will get some weak formulation. And after that, we will go for temporal discretization. So in this scheme, we are using some Runge-Kutta scheme. And later, we will apply, we have to choose some appropriate basis function. So in this basis function, we are using orthogonal basis function, which based on the Legendre polynomial. So now we'll go for result discussion part. Because since Boltzmann transport equation is not easy to solve complete like analytically, so we will go for some approximation. At first, I'm solving for 1D Boltzmann transport equation. We have some assumption. At first, we are assuming that electrons are homogeneous. So this part is 0. And in 1 dimension, there is no magnetic field. So we assumption is 0. Then velocity in momentum space is become a function of electric field. And for scattering term, we are using reaction time approximation. In this one, 1D Boltzmann transport equation is become in that format, where F0 is a local equilibrium distribution function and tau is the extinction time. For electron distribution function, we are using Fermi-Dirac distribution function as the initial condition. For 1-dimensional cases, we are taking tight binding distribution energy dispersion relation. Basically, electric field we can be classified in 2 formats. One is time independent, one is time dependent. So I'm taking 2 different cases. At first, let's go to steady state solution at when the electric field is constant. So we can write we are driving here analytic solution for Boltzmann transport equation at steady state. We will describe that solution of distribution function. We can write in the expression of some corrected perturbation. We will get some these values when we will insert this equation into the Boltzmann transport equation. Similarly, we will get for some high electric field analytical solution. This is the validation for numerical solver when electric field is constant. When electric field is very low, we can see here, this is a numerical solver and analytical solution. We are good agreement. And we can find here the change in the distribution function is completely near the equilibrium. When electric field is goes very high, suppose we are going to 10 power, this is 1 lakh electric field, some value, very high value. We can see here, when electric field is very, very high, that electric field become almost constant. When electric field is decreasing, then we can find some kink in the numerical solution on the population. And we can see here that numerical solver is well in good agreement with the derived analytical solution. This is a movie when for dynamics of Boltzmann transport equation. This is the when electric field is very low, then you can see some the changes in the distribution function is very small and is completely near the equilibrium. When electric field is very, very high, then system goes to the Bloch oscillation region, and after that, when scattering term occurs, then it damped, and this is the solution next. Now we will go some effect of constant electric field on Boltzmann dynamics. When electric field is very low, then you can see here some solution. This is nearly completely near to equilibrium. When electric field is high, then you can see here when the electric field is constant and very, very high, then population become constant. This is the effect of inverse temperature on the Boltzmann transport equation. When the beta is defined by 1/kBT, it means inversely proportional to the temperature. When beta is 1, it means temperature is very high, then population become very smooth. And here electric field, the effect of electric field is very negligible. But in case of when beta is very high, it means temperature very low, we can find some discontinuity in the solution, and then solution goes to the damp Bloch region. And you can see here, after that, it becomes steady state. Generally, when the solution has some discontinuity, most of numerical methods become fail. And in this situation, we can say that this numerical method is very accurate and very good. This is some effect of electric field on the current density. You can see here, this is the time scale, and this is the electric current. When electric field is very low, then before reaching a steady state solution, it's going slowly. While when electric field increased, then before reaching a steady state solution, we have find some jump, because solution is going to the in Bloch oscillation region. That's why we have some jump here. Similarly, when at a high electric field value, it has some transition phase in the high frequency solutions. Now we will go the time dependent electric field value, and we will find some analytic solution. So in this situation, we have some 1D Boltzmann transport equation. In this equation, we can write the solution in the part of imaginary part in this format, and then we will get some conductivity in this mathematical formulation. And you can see here even order conductivity when it's due to symmetry. Now we will validate our numerical solver with analytical derived conductivity. Then here these are 3 images where this line is the magnitude of the conductivity. This is the real and imaginary part. You can see here we found 3 first, third, and fifth order conductivity, and the numerical solution is very close to the analytical solution. Now this is the effect of time dependent electric field, same like constant electric field value. Here we have get the Boltzmann dynamics at low and high electric field value. And here that this is a solution of the electric field at high. This is similarly for effect of inverse temperature, and we will get here the dynamics of Boltzmann equation at different of beta's value. Similarly, we get some solution have a different value of chemical potential. Here we can see here that solution goes to the electron to hole region. After that, we will get some electric current density at time-dependent electric field. And now, after that, now we are working on 2 times the Boltzmann transfer equation. This is a Boltzmann transfer equation. Here, we are solving this equation with reaction time approximation for homogeneous electron. So we can write the Boltzmann equation in this formulation, where Vx and Vk defined by in this mathematical expression. We are using Fermi-Dirac distribution function, and for energy dispersion relation, we're taking tight binding energy dispersion relation, and this is the picture of this assumed functions. Now we will get analytic solution for the steady state Boltzmann transport equation. In this equation, we can write the Boltzmann transport equation in this format. And after substituting this equation in the Boltzmann transport equation, we will get the final analytical solution. After that, we validate our numerical 2D solver with 2D Boltzmann at steady state, and we found that our numerical method is very close to the analytical solution. And this is the time evolution of Boltzmann transport equation. And we can see here when the time is goes, then solution goes to the Bloch oscillosum region. And this is the solution of in one-dimensional form. And after that, we calculate electrical and hole conductivity in Boltzmann equation. When the magnetic field is applied in z direction, we can write the current density in that format. We have Jx and Jy is the electric current in the x and y direction. Here, sigma xx and sigma y is the electrical conductivity, and sigma x and sigma y is the hole conductivity. Hole conductivity we can get without implementing electric field in y direction. So we can take Ey equal to 0, and then we can get hole and electrical conductivity by these mathematical functions. So this is the profile of normalized electrical and hole conductivity with respect to the electric field. And here we are seeing here when magnetic field is increasing, then hole conductivity and electric conductivity is decreasing at low temperature. But when electric field is increased, we found some kink in the solutions, because solution is going to the Bloch oscillosum region. And finally, I am working on 3-dimensional Boltzmann transport equation. And after that, this is my summary. We developed a DZ method solver for solving multi-dimensional Boltzmann transport equation. In Boltzmann transport equation, we are taking simple scattering operator, namely reaction time approximation. Then for validation for numerical solver, we type some analytical solution. And this work will be extended in high dimensional cases, especially interest for strongly out of equilibrium for real application. This is my talk. Thank you so much.
Okay, thank you. Let's have some questions from the audience. Any questions?
I just have a very quick kind of query in a sense. Yeah. So is it like the solution? Is it like, you showed that you have applied this sinusoidal kind of electric field or like that one. So I'm just asking, like, if we change this electric field to a different form or like that one, whether the solution process is like the same, or I mean, in a sense, the calculation process I just want actually.
The numerical same, exactly everything is the same, but we tested the electric field for different values, and it's applicable everywhere. So the numerical solution, this numerical method will work for every type of electric field value.
I see. Okay.
Okay. Any other questions? Maybe a quick question is, I suppose the numerical method you have developed can also calculate the one in our first talk when people discuss about this relaxation time of the photovoltaic effect. Can you do this kind of calculations? For a special particular, it can be a quite complicated band system with non-trivial topology or non-trivial symmetry. Can these be incorporated as physical parameters in your calculation, and you can predict certain kind of relaxation time that may have interesting dependence on the symmetry and topology of the system, right?
Yes. This is our future work. We will go according in the direction. Yes, and we will go for real-time application. Yes.
Okay, that's great. That's very interesting. Okay. If there are no more questions, I think we're going towards the end of today's session. I will give a sharing session of my research. I know it's been a long day. Okay, so let me just share my screen. I think we'll just do it casually. It's a long day. Okay, so yeah, I hope to finish it maybe in half an hour or something or less. But feel free to leave if you have to. Okay. Okay. So also, I'm trying to make this a presentation that is focusing more on the conceptual ideas instead of the technical details. If you're interested in the technical details, you can always talk to me or look at some of the papers here. Okay. I think you can all see my screen, right? So I'm going to share with you some of my recent research on the dynamics of anyons in fractional quantum Hall systems. So I will start with a brief overview of the quantum Hall system, and I'll talk about how anyons can emerge from such systems, and in particular, why fractional quantum Hall system can be a very natural platform for the experimental realization of quantum fluids, where anyons are the elementary degrees of freedom. Then, of course, I'll talk about some of the interesting physics when anyons start to interact with each other. Okay, so I think you all know about the Hall effect, the Hall bar. The quantum Hall effect is realized in a 2D Hall bar, where you have a 2D electron gas system, and when you inject electrons in one direction due to the Lorentz force, there is charge accumulation in the perpendicular direction, and that's a voltage. Right? So you can define this interesting quantity called the Hall resistivity, which is voltage along one direction divided by the current in the perpendicular direction. So Hall coefficient is coming from the Hall resistivity divided by the magnetic field. And this gives you the inverse of the charge density of the system, as you can calculate from basic Newtonian mechanics. So naively speaking, this is actually a very simple physical system. We're not really expecting any interesting or deep or fundamental physics coming out of it. And let me explain why. So imagine if you're a person in a lab looking at a very large piece of metal with a perpendicular magnetic field. So this is a 2D electron gas, and nothing's really happening here. Then you can always jump into a cart that is moving at a velocity relative to this piece of metal. So formally speaking, you're boosting yourself into a different inertial frame. And in this new frame, you can look at the same piece of metal again, and of course, you'll be seeing a current since all the electrons are moving with respect to you. And due to the Lorentz transformation of the magnetic field, in this new frame, you'll also be seeing this electrical field in this direction. Now, assuming that your velocity is much smaller than the speed of light. So to the leading order, E is just equal to V cross B, so it's V times B here. So from your observation, there is a specific fixed relationship between the current in one direction and also the electrical field in the perpendicular direction, leading naturally to this Hall coefficient equal to the inverse of the charge density. So the message here is that you really don't need to know anything about classical mechanics like Newtonian mechanics or Lagrangian, right? You don't really need to know anything about quantum mechanics and definitely not the topological physics. The fundamental symmetry of our universe, the Lorentz invariance, which is basically how the magnetic field is defined in the first place, dictates that if you do a measurement of the Hall resistivity in this system, the only information you can get out of the system is the charge density of the system. And what else can you get, right? So imagine a surprise when people actually do this measurement, And of course, at low magnetic field, that's what we see is what we're expecting. You have a straight line where the gradient of the Hall resistivity gives you the charge density. But at high magnetic field, you see these plateaus forming, and these are so-called integer quantum Hall effect. And these plateaus are remarkably accurate. They correspond to a fully filled Landau level, where Landau levels are coming from the energy spectrum of a single particle Hamiltonian in a magnetic field. We even use this kind of measurement to define the unit of resistivity because they're very accurate. Now, of course, we understand this is something topological, but what happened to our original argument with Lorentz invariance, right? So the reason why we see these plateaus is, first of all, at the integer filling factor, we have a ground state gap. It needs a finite energy cost to put another electron in a higher Landau level because of the magnetic field. The second important feature is because of the presence of disorder in the system leading to Anderson localization. So when you are deviating a little bit from the integer filling factor by, for example, putting some charge carriers in a higher Landau level, they will be localized by the disorder and they will not contribute to the Hall conductivity. On the other hand, there's also an obstruction of Anderson localization due to the presence of the magnetic field. So in this case, Anderson localization cannot localize everything. You can't localize the edge current, and that is topological. That explains why these plateaus are very well quantized at these particular values. Okay, the reason why our original argument was boosting into a different inertial frame fails because we assume translational invariance there, and in real systems, we do have disorder breaking that symmetry. Okay, so the presence of the plateau is because, first of all, we need to have non-zero disorder in the system. And second of all, this disorder has to be much smaller than the ground state gap. And these two factors are necessary for the experimental revelation or to experimental observation of these topological features, but they are not required for the topological features. So the topological feature is always there, but to see it in experiments, you need to have these two things. That's the main idea. So the integer quantum Hall effect is really a single particle effect, or everything can be explained by the single particle Hamiltonian. But later on, when people go on to a larger magnetic field, they observe these plateaus forming at the places where a single Landau level is partially filled. For example, it's a 1/3 field or 2/5 field. In this system, of course, we still have Anderson localization, and we still have obstruction to the Anderson localization due to the magnetic field. But the main question here is that where does the ground state gap come from? That is also a necessary ingredient, right? It cannot come from the kinetic energy because we have a partially filled Landau level, so it is gapless. So the gap can only be coming from the strong interaction. So these are the fractional quantum Hall effect, which is a physics when arises from a strong interaction between electrons. And when electrons start to interact strongly with each other, they lose their own identity. Right? You don't really see an electron anymore, and you see a lot of collective excitations leading to very interesting physics in here that can be observed if you have a gap to the ground state. So this is a long way from our original picture with only the Lorentz invariance. Right? It turns out that this can be a very rich system with many interesting physics. And the underlying mechanism of this gap can be very different for different filling factors. Just like in superconductivity, you can have different mechanisms of pairing to form superconductors. The BCS theories and for the high temperature superconductors, they can be very different. Right? Okay. So what we're going to focus on today are the anyons. And I think you all know about the anyons. In 3D, we only have bosons and fermions because a loop can always be contracted to a point. But in 2D, a loop that does not enclose a particle cannot be smoothly deformed into a loop that is enclosing a particle. Right? So in 2D, the exchange phase, Berry phase, can be any real number instead of just 1 or +1 when you exchange the two particles. Okay, so let's talk about anyon a little bit. So this is basically a more formal outline. The first part, I'm going to talk about some of the formal development. Then the second part, I'm going to talk about some of the experimental predictions. And the third part is again formal, and let's see if we have time to do that. Okay, so let's go back to the integer quantum Hall effect. Where is the physics of topological structure coming from? Right? Starting from a band system with continuous energy spectrum, when you apply a magnetic field, of course, you form Landau levels. Okay, so the Landau levels have energy spacing that can be much larger than the temperature. So the integer quantum Hall effect comes from the fact that the only accessible Hilbert space is a single Landau level. All higher Landau levels are forbidden because of the high temperature. It is because of this truncation of the Hilbert space that leads to the topological structures, for example, the Hall conductivity, quantization, and the Luttinger liquid description of the edge excitations, etc. So this is actually an example where the universal properties of a system are defined by the special structure of the Hilbert space algebra, here a single Landau level. And these universal properties are the topological properties. So if you start from a full Hilbert space, in a full Hilbert space, of course, the elementary degrees of freedoms are the electrons, which are point particles. But once you project into a single Landau level due to the Hamiltonian, you are losing a lot of information. You can't access all those higher Landau levels. So the measurable degrees of freedoms are actually not the electrons anymore, but quasi-particles, which are not point particles anymore, but they are something like a Gaussian wave package. You never know exactly where the quasi-particle is. It's fuzzy because of the loss of information. Formally, that's because of the non-commutativity of the coordinates in a single Landau level. Right? But these quasi-particles are still behaving like electrons because they have the same charge of the electrons, and they behave also like fermions. But this is the overall picture, which is universal both for integer quantum Hall effect and also fractional quantum Hall effect. So for integer quantum Hall effect, we're talking about states living in a single Landau level. But for fractional quantum Hall effect, due to the Hamiltonian, there can be a further truncation of the Hilbert space. We're talking about the states living in a smaller sub-Hilbert space with also rich algebraic structure. So for example, for the Löffling state, it lives within this particular sub-Hilbert space where the interaction makes all other states outside of that Hilbert space to be energetically not favorable and not accessible at the low temperature. So this further truncation of the Hilbert space leads to the new topological properties of the fractional quantum Hall effect, and each of these Hilbert space corresponds to one particular type of anyons. You don't have electrons or quasi-particles anymore because you have further lost a lot of information. Okay, so these Hilbert spaces are special in a sense. We call them conformal Hilbert spaces because they have conformal symmetry and bulk edge correspondence. So there are many different ways of understanding a conformal Hilbert space. The simplest way is to know that in a conformal Hilbert space, there's one highest density state. Okay, this state corresponds to the ground state of fractional quantum Hall effect, describing a 2D quantum fluid, and all other states in this conformal Hilbert space are actually the excitations at the boundary of this 2D quantum fluid. Now, if you look at the ground state and look at the entanglement spectrum of it, there is actually a one-to-one correspondence to the counting of the entanglement spectrum to all of the other edge excitations in the Hilbert space, in this particular Hilbert space. That's a very important structure, which is the reason why we call there is a bulk edge correspondence or holographic description in this particular Hilbert space. And it can be constructed by the conformal symmetry, but that's something that we don't have to go into now. Okay, so this is a conformal Hilbert space. Now, the key idea here is that for each conformal Hilbert space, when it is properly defined, it corresponds to a particular type of anyons with a particular property, like its charge can be different from electrons and its exchange statistics can be different from electrons, which is why we call it anyons. Okay. So now let me just introduce something that can be quite interesting. It's one of the more interesting things that I discovered in the past 2 or 3 years, the so-called local exclusion conditions. This is particularly useful if you have never really studied fractional quantum Hall before, because fractional quantum Hall requires a lot of background knowledge and different approaches in understanding it. But this LEC can be arguably the simplest way for us to understand fractional quantum Hall effect in a very general picture. Okay, so the LEC is defined by a triplet of integers. What it means is that if you have a quantum fluid, any quantum fluid that is translation invariant, you can look at a circular droplet in this quantum fluid. And this circular droplet can be of roughly the area of 2 pi n LB square, where n is the integer here. So it contains n magnetic fluxes, and LB is the magnetic length of the system. Okay, so we can talk about what happens if we do measurements in this droplet. The LEC tells you that certain things you can't measure. So if you do a measurement in any circular droplet of this particular size, this quantum fluid, you can never measure more than NE number of electrons, and you can never measure more than NH number of holes, which are empty orbitals. So it is really a statement on a classical constraint on what you cannot measure from the quantum fluid. It is a constraint as a reduced density matrix of a particular quantum state. It turns out, if you look at all valid quantum states satisfying a particular LEC, all these states span the conformal Hilbert space with this very, very well-defined algebraic structure. So it actually corresponds to a particular phase of the fractional quantum Hall effect. The interesting thing is how general it is. You can actually describe almost all of the fractional quantum Hall states, including the abelian ones and also the exotic non-abelian ones, by just one physical input. This physical input is dictating what you cannot measure from a quantum fluid in a circular droplet. Okay, and this LEC condition allows us to unambiguously determine all of the topological properties we can think of for a particular topological phase in a single Landau level, including the ones I listed here. Okay, it can also provide a very simple numerical way of generating the ground states and also quasi-Hall states of even very exotic topological phases that are otherwise not easy to get numerically using other methods. Okay, so that's something that is interesting, but conceptually speaking, it is the most general way of defining a conformal Hilbert space. Okay, and we know every conformal Hilbert space corresponds to a particular type of particle, which is the anyons. It also even predicts many new conformal Hilbert spaces that people didn't really know before. Okay, so also it gives you a way of reinterpreting interaction Hamiltonian in a strongly interacting system and rewriting it into a virtual lattice in a continuous system. So this virtual lattice is so-called von Neumann lattice, where the spacing is on the order of the magnetic length. But each lattice site is a projection operator. And this projection operator can involve more than one particle. And when they involve more than one particle, one can prove analytically this is equivalent to an interaction Hamiltonian coming from, for example, Coulomb interactions or some special interactions. But really, you can map a fractional quantum Hall effect into a continuous version of the AKLT model, where you have a summation of projection operators in the real space in a frustration-free manner. And from a mathematical physics point of view, this can potentially be helpful in improving the incompressibility of certain model Hamiltonians. It also allows us to think about some new ways of experimentally realizing this fractional quantum Hall effect, not by tuning the interaction, but by realizing a lattice of projection operators in real space for continuous systems. Okay, so the general idea now is that topological properties come from the Hilbert space algebra. So starting from electrons, when we confine into a single Landau level, we get quasi-particles, which are like electrons, but not point particles. But if we further confine ourselves to some conformal sub-Hilbert space by means of interaction, right, then the only accessible degrees of freedoms are now anyons. They are even fatter particles because you're losing more information. And more importantly, they can carry different charge from electrons. And they can also have very exotic exchange statistics, which is why we call them anyons. And that's how anyons emerge from, they simply emerge from the Hilbert space algebra. Interaction or Hamiltonian, either kinetic energy or interaction, is just one way of realizing this truncation of the Hilbert space. And so the anyons becomes the fundamental degrees of freedom in these sub-Hilbert spaces. Okay, let's see how useful these things can be. Right, so we talk about the Löffling phase because Löffling phase is actually the simplest fractional quantum Hall phase, first discovered in experiment and very extensively studied in the literature. But it turns out what we found is that even for this very simple Löffling phase, there are very interesting rich dynamics people didn't know before. Right, so this is a particular phase that is defined by the Löffling Hilbert space, the conformal Hilbert space, using some pseudo potentials or LEC. So in realistic situation, if you have a short-range interaction from Coulomb interactions in the lowest Landau level, then we know this Hilbert space is a very good approximation of the real Hilbert space with a non-ideal Hamiltonian. But we also know that in higher Landau levels, when the interaction becomes more long-ranged, the low-lying excitations are no longer described by the Löffling Hilbert space anymore, even though we still believe we are looking at the same topological phase. So what is really happening here? Right? So this is also something I think Tron gave a nice presentation to at the beginning of this year in our first theory day sessions. So we have done a lot of numerics one way or another to show an interesting fact that with the second Landau level Coulomb interaction, a realistic interaction in higher Landau level, the low-lying excitation are no longer living within the Laughlin Hilbert space, but is living within a different fractional quantum Hall phase called the Gaussian Hilbert space. It's an enlarged one, right? We do this by looking at the wave function overlap and also, for example, looking at the variational energy of the spectrum. I'm not going into the details here, but the message is that we show very convincing numerical results that the low-lying excitations can be thought of as quantum fluids of not the Laughlin quadriholes, but the Gaussian quadriholes. The Gaussian quadrihole is just the anyons in the Gaussian conformal Hilbert space. Okay, so there are some technical details I'm not going into here. So we're looking at these states more carefully using some mathematical tools that are popular in fractional quantum Hall literature. So the main idea is that if you look at the Gaussian Hilbert space, the ground state is the vacuum where there's no quadrihole anyons at all. Right? We create quadriholes or anyons by inserting magnetic fluxes into this vacuum. And the Laughlin state is obtained in this way. So we can think of the Laughlin ground state as a quantum fluid of Gaussian anyons or Gaussian quadriholes. So starting from the Laughlin ground state, we can insert another zero here, which is another magnetic flux. So we are creating either, we can think of it as creating one Laughlin quadrihole, but in this picture, we can also reinterpret it as a pair of Gaussian quadriholes, because it's still a quantum fluid of Gaussian. It lives within the conformal Hilbert space of the Gaussian state. Right? Okay, wait a minute. So the key idea is that the Laughlin quadrihole actually has an internal structure. You can think of this as a molecule or bond state of one pair of Gaussian quadriholes with internal levels from this picture. So this is very natural to see from the conformal Hilbert space point of view, but why didn't people really talk about this before, right? And people study Laughlin states for a very, very long time. And so let's analyze what happens when we pull this pair of quads. We have one pair of quadriholes, we can pull them apart, right? We can construct many body wave functions when we slowly pull the two quadriholes apart. And no matter how they are apart from each other, these are still states living in the Gaussian conformal Hilbert space. So they're still Gaussian quadrihole states. But when you're pulling them apart, what happens is that in between the two quadriholes, you create these Laughlin neutral excitations, like the density modes for the Laughlin state comprising of one quadrihole and one quadri-electron. So these are the Laughlin quadri-electrons. Okay, so this is what happens using the Jack polynomial formalism, which I'll not go into details here. So with these states available, we can look at their variational energy and to understand the interaction between the two Gaussian quadriholes. And this is what we get, which is quite interesting. If we look at the short range interactions, like the one very close to the Coulomb interactions in the lowest Landau level, then it turns out the further you pull the two quadriholes away, the higher the energy cost, as you can see from here. This is because you are creating more and more neutral excitations in between the two quadriholes, and each neutral excitation costs a finite amount of energy, because for short-range interactions, the Laughlin state is gapped, right? There's an energy scale in there. So this is actually very similar to the quark model, where you have asymptotic freedom when the attraction between the two quarks are getting stronger and stronger when you pull them apart. So these Gaussian quadriholes are analogous to the quarks, and the interaction between them are mediated by these neutral excitations that are bosonic. So they play the role of gluons, mediating the interaction between the two quarks. So, which is why in experimenting theory, when we talk about short-range interactions, we never talk about fractionalization because they are like protons, right? You can't really pull them apart because of asymptotic freedom. They always bond together when you have a short-range interaction. Okay, but if you look at the more longer-range interaction with a so-called pseudo-potential formalism, then for longer-range interaction between electrons, the interaction between the Gaussian quadriholes become repulsive, as you can see from here. So it is actually energetically more favorable for you to pull them away from each other. Okay, so that actually hints at the possibility of the fractionalization of Laughlin quadriholes, even in second Landau level, because we know in second Landau level, the long-range component is much stronger as compared to the lowest Landau level. So from at least from a theoretical point of view, we can propose this a mechanism of fractionalization of Laughlin quasi-hosts leading to a different type of charge for the elementary excitation. But of course, this is not really seen in experiments so far. So it could be because V3 still lose to V1 for the second Landau level. But let me show you that this is actually something that can be very experimentally relevant. Okay, so this is actually related to an interesting phenomenon called the nematic fractional quantum Fourier effect in the strongly correlated systems. So this is where we're not talking about the universal properties, but we're talking about the interplay between the topology and emergent geometry in this two-dimensional system. And let's look at experimental data, right? So under certain conditions, what people see in experiment is that there can be a coexistence of the quantum Hall plateau, indicating there's a charge gap in a system that is topological, but also an anisotropic transport for the usual longitudinal resistivity along the x direction and y direction. What is surprising is that at low temperature, this anisotropy is enhanced, indicating some kind of a phase transition at low temperature in coexistence with the topological order for the ground state. So this has been extensively studied in theory because it itself is a very interesting theoretical question. So this is the energy spectrum of the Laughlin state, where you have a ground state here, and you have a dipole excitation gap, which is basically the charge gap coming from a pair of quasi-Hall and quasi-particle. But for this elementary Bronschow excitation in the long wavelength limit, we have this quadrupole excitation, which are the density modes of the fractional quantum Hall that is gapped, and it has no dipole moment. Okay, so the key message here is that the quadrupole excitation and the dipole excitation are two different types of the excitations in such system. So the dipole excitation gives you the charge gap, but the quadrupole excitation is a neutral gap. And the nematic fractional quantum Hall is believed to arise from the fact that the charge gap is always open. So that's why you always have quantized Hall conductivity, but the neutral gap becomes gapless, leading to some kind of a spontaneous symmetry breaking and anisotropy of the ground state. But it does not affect the charge transport. That's why you still see the Hall plateau. Okay, so theoretically, the interesting question is how tunable are these two energy scales when you tune the bare interaction between the electrons. So we have done studied this very extensively for many different ways. So there are some analytical derivation of the energy gap in the long wavelength limit of this quadrupole mode. People also call this a graviton mode because it's coming from the metric fluctuation. And we also do numerics based on the analytical derivation to show the phase transitions. And more recently, my student Yu Zhu and I also come up with a more analytical mathematical proof of some of the statements that are important in what I'm going to say later. So it's a very nice combination of analytical derivation, numerical calculation, and mathematical proof. And the final result is that we can construct this minimal model Hamiltonian in capturing the transition from the fully gapped Laughlin phase to the nematic Laughlin phase, where the neutral gap is closed, but the charge gap is still open. Okay, so this is the model Hamiltonian in here. Okay, why is this related to the fractionalized charge of Laughlin quasi-host? Because we also realize the same model Hamiltonian, based on our understanding of these wave functions, is also the model Hamiltonian in describing the fractionalization of the Laughlin quasi-host, the two competing energy scales, right? One is binding them together, one is trying to separate them together. By tuning these two Hamiltonian two components, you can model this type of transition. So the main message is that the softening of the neutral excitation in the Laughlin state is closely related to the fractionalization of the quarks, of the protons in some sense. And so when this energy scale becomes smaller than the temperature, then it's energetically favorable for Laughlin quasi-host to be split into two. So that's the main connection between the two physics. So we predict a particular type of phase transition at finite temperature. We don't really require the neutral excitation to go soft as long as it is smaller. So as long as it is smaller than the temperature, then there is a KT-like transition where a certain fraction of Laughlin quasi-hosts can split into two leading to a charge of 1/6 of the electron charge that can be observable in the experiment. Okay, it is not easy to observe in usual quantum Hall systems, but since people have already observed nematic fraction quantum Hall in experiment, right? So what we're proposing here is that if you can see nematic fraction quantum Hall in the neighborhood of that particular phase, we should be able to see many fractionalized charge of the Laughlin quadrico carrying a different charge and of course different statistical properties. And it is an interesting phase transition because it's a phase transition where the ground state topological properties are invariant, but the low-lying excitations undergo some qualitative transition and even topological transition, leading to observable effects. So this is the main message of the anyons when they start interacting with each other. Okay, so still have some So some conditions we derived in the experiment so that needs to be satisfied in the experiment for such phenomenon to be seen. Okay, so for the last part, I'm going to talk about a more formal thing about this anion boson duality, which is also related to the properties of the anions. As you can see, anions are very natural and the only accessible elementary degrees of freedom for a fractional quantum Hall system. Because the interaction is projecting out part of the Hilbert space, you are left behind with a conformal Hilbert space. The conformal Hilbert space on the has very interesting properties. The first interesting property is a bulk edge correspondence, as I mentioned before. So when you're creating a quasi-Hall in the bulk by inserting a magnetic flux, because of the non-vanishing Hall conductivity, you're really pushing electrons away from the flux, leading to excitation at the edge. So every excitation of a flux insertion can be either interpreted as a bulk excitation or interpreted as an edge excitation. And an edge excitation is a 1D chiral liquid, which we know we can bosonize, right? So we can bosonize the edge excitations, but we can also do a conformal mapping from an open boundary condition system to a closed boundary condition on a sphere, for example. On a sphere, we still have these quasi-Hall excitations, but they can't be reinterpreted as edge excitation anymore because there's no edge, right? These are really bulk excitations, very well localized in the bulk. But because of this correspondence, in principle, we can also bosonize these excitations in a 2D manifold. It's a 2D bosonization, and we're not just talking about any fermions here, right? We're talking about anions, because if you look at the fractional quantum Hall Hilbert space, anions is the only physical thing that you can talk about. Okay, so we basically developed this particular microscopic formalism in bosonizing elementary degrees of freedoms in a conformal Hilbert space. And this elementary degree of freedom can be either fermions, if you're looking at the integer quantum Hall effect, or anions, if you're looking at a fractional quantum Hall effect. This can be made rigorous, okay? So I won't go into the mathematical details, but by matching the quantum numbers and making sure the quantum number represents quasi-particles, we can really just define a basis transformation. Where on one side, the bases are the anion bases, on the other side, the bases are the bosonic bases, and this is a well-defined unitary transformation from one side to another. So really, a linear combination of anions can behave like bosons. That's the key message. Okay. This also allows us to write down dual descriptions of fermionic fractional quantum Hall. So I will not go into the details here, but let me just give you the main message is that for any fractional quantum Hall effect in the fermion basis, we can come up with a dual description or in a bosonic basis. This leads to the prediction of many new bosonic fractional quantum Hall effect. And the interesting thing is we are actually rewriting anions in terms of bosons, right? So bosons are much simpler. Bosons are really the simplest possible particle. Fermions are still interacting because they have statistical interaction. Right? Bosons, they really don't know each other if you don't have other interactions. So if we are converting anions to bosons, we must give something, right? We can't just simplify the system. It turns out what we give is a much more complicated interaction. So if the anions or fermions have very simple interaction, when we convert it into the basis of bosons, we have very complicated interaction because this interaction has to account for the statistical interaction between the original particles. But this is actually a formal way of writing down these complicated statistical interactions into a microscopic Hamiltonian. involving pseudo-potentials, a very useful tool in fractional quantum Hall. So people study about statistical transmutation quite a lot by flux attachment, etc., in the effective field theory description. But we don't really can't really do much to it. Right? We can't even do much with perturbation theory, like Feynman diagram, etc., because it's a very complicated procedure in attaching fluxes to particles. But here we can derive a very concrete mathematical form of the microscopic Hamiltonian, something we can actually do numerics and whatever calculation you want to do. And we can show that indeed, with this dual Hamiltonian in the bosonic basis, it has exactly the same spectrum as the fermionic basis. This is very similar to the plot I showed you just now with the laughing state. But this is a bosonic picture that a very different filling factor and different shift. So it's a totally different state, but we can define a model Hamiltonian to it. Okay, so yeah, I think that's pretty much everything I want to talk about. Just to give you a taste of some of the interesting things can go on in these new platforms. One can imagine, so this is a summary slide. So one can imagine that we are now coming up with a platform where the elementary particles are not electrons but anyons. You can really do a lot of study to it, right? So think about anything you can think of about the electron fluid. Even for many-body localization, etc. You can think about, can they be applied to an anionic fluid where we have a very good way of generating the Hilbert space, the many-body microscopic wave functions, etc. And we can study all interesting properties of it. They are very much experimentally relevant because at least for the simple fractional quantum Hall states, we know how to realize them in experiment. Okay, I guess that's all. I don't know how much time I took, but if you have any questions, I'm happy to answer them before we end the session.
I had a small question. So I this, but what's the origin of this local exclusion constraint or condition? It seems like a lot of the stuff is basically flowed from that, right? That was
right.
So how do I understand that the local exclusion principle or condition? I can't remember which slide it was. Must apply or is true.
Okay, so well, in terms of the justification of that,
slide 15.
Slide 15. Yeah, I know, yes, but I'm trying to show you this slide actually. Okay, so this is sort of the fundamental idea behind the LEC. So this slide is basically saying that the topological properties are defined by the truncation of the Hilbert space. It really depends on how you truncate the Hilbert space. So the property of the remaining Hilbert space that is accessible physically defines the topological properties as well as the anyons, right? So what is LEC? LEC is really telling you that there is a constraint on the reduced density matrix. By this constraint, you are basically saying that certain states in this quantum fluid is not accessible. Okay, so this is a very general scheme of truncating the Hilbert space. And it turns out from a numerical analysis that this particular Hilbert space truncation gives you exactly, not just the finite size scaling, but for any system size we can access, give you exactly the model wave functions for the ground state and quasi-hosts. Okay, so we all know, in some sense, in the fractional quantum Hall community, that the topological states have very special entanglement spectrum. Right? So they are in particular missing states in the entanglement spectrum, exactly coming from the truncation of Hilbert space. So these missing states are basically telling you that certain things are not you can't really measure, right? Because it's a property of the reduced density matrix. So what is surprising here is that if you just look at reduced density matrix of a very small unit, and in this case, there's only one or two missing states. But as long as you have this one or two missing state incorporated into the constraint of the Hilbert space, everything emerges from it. Okay? It's very well defined and unambiguous. So I don't know if that answers your question, but this is an experimental observation. There's no analytical proof, many of the things for the Jack polynomial, etc., really, we can't really prove it analytically, but it's very robust in the sense that it's not finite size scaling, it's just 1 or 0, right? We see this is true for any system sizes. So we conjecture it's true for all system sizes. The only physics I can think of here is that really topological properties are coming from truncation of Hilbert space. It really depends on how you truncate the Hilbert space.
So if I might push a little bit, is this sort of related a little bit to your first slide on Lorentz invariance, right? So if I look at equation, slide 15, if I go to slide 15, if I go to slide 15, and it says that, you know, when I look at the reduced density matrix,
right,
I can only, the only things that I can definitely measure are N and E and H.
Yes.
And that's all I can get out of this kind of thing. Is this somehow related to your idea in the first slide, whereby you say that if I now have some kind of Lorentz invariance of a quantum gas, and then I boost to a high velocity frame in which there's the magnetic field kind of stuff, I can only measure density anyway. So this is kind of a kind of projected onto a single band limit type of analog.
Well, I would say it's not really that the case. So the example here, right, is basically saying that when I do measurements, I only get the charge density, but the topological structures are still there. Right? So let me just maybe show you this slide. So if we have Lorentz invariance in a translation invariance system, when we do measurement, what you'll be seeing is an entire region to be a straight line. Okay? There are no plateaus or anything. That's what is predicted, and it should be true. It doesn't really mean that those points at the integer filling factors are not special. Right? These are still special points along this line, but this particular measurement cannot reveal these special points. The topological structure is still non-trivial at mu equals to 1 or 2 or 3 or 4, but you can't distinguish for those points from other points just by looking at the whole resistivity. I think that's the only idea conveyed by the original argument, which was first brought up by Steve Gervin in his Zeus lecture, which is a very interesting argument. So in my LEC description, I'm assuming translation invariance. So in this particular system, I'm trying to understand the topological property of the system, but I'm not trying to understand, I'm not predicting the evolution of the plateau in this system. That requires disorder, right? So there are two things in here. So first of all, the plateau itself is not in some sense related to the topological structure. The plateau is really just a way for you to see the topological structure in this particular simple measurement. And that only is the point I want to make in saying that why the original argument is wrong. But what I'm trying to study is some topological properties that are both present, both with or without disorder. And that is what the REC is about. So it's really talking about the topological physics, where here we don't need to know anything about topological physics. I'm only trying to say something about a particular experimental measurement, which will not give us any information about the topological physics. I don't know if that makes sense.
Yeah, so maybe I extrapolated a bit too much, but yeah, great. Thanks.
Yeah, okay. Okay, any other questions? If not, I guess, yeah, it's been 12 o'clock. So thank you very much, everyone, especially to the speakers. And again, I encourage you guys to talk to each other offline and to see if there can be some synergies coming up. Right. So our next session is on July the 13th, and I think it'll be in the afternoon. We're going to try it in the afternoon. And Professor Li Qinghua is also going to give a talk at the end of the session. And we'll make more, make announcements